Hello students. In this video lecture we will discuss about the Prim's algorithm, which is used to find out the minimum cost spanning tree for any given weighted undirected graph. So first of all, introduction of the Prim's algorithm. This algorithm was developed by Wojtek Jarnik, who is a mathematician, and in 1957 it was rediscovered and republished by the Robert C. Prim. And after some years, it was also redesigned by the mathematician Discastra, who have also invented the shortest path algorithm. This is a greedy algorithm in which the final minimum cost spanning tree is obtained in different successive stages. And this algorithm is applicable for a weighted undirected graph. Here we have to select a vertex in a random way, means we can select any vertex of the given undirected weighted graph as a start vertex, and then we start our processing, and every time at every stage we add a new adjacent vertex to this start vertex to our tree, and those vertex is selected, that vertex is selected which has the cheapest edge. Its performance is very good in case of dense graphs, means we can get the faster results if the graph is a dense graph. Now that time complexity, if we use the binary heaps, then the time complexity of the Prim's algorithm will be big O of E log V, but it can be reduced to big O of E plus V log V if we use the Fibonacci heap. Now the statement of the Prim's algorithm. Uh, we have to select a arbitrary vertex to start the procedure, and suppose this arbitrary start vertex is Vi. Now we have to find all the adjacent nodes or vertices of this vertex Vi, and that vertex Vj is attached to this vertex Vi, which has the cheapest linkage with Vi, means which is attached to a cheapest edge. Now the next step, when Vi and Vj are added, we consider Vi and Vj as a subgraph, means as a single unit, and we find the neighboring nodes of this whole system, means whole subgraph Vi and Vj. And for this purpose, we have to find all the neighboring vertices of Vj and all the neighboring vertices of Vi, then take union of those vertices, and that union gives the all the neighboring vertices of this subgraph Vi Vj. Suppose next time a vertex Vk is attached to this subgraph Vi Vj, then we have to take this Vi Vj Vk as a new subgraph, and step 3 is repeated until all the vertices are connected. And when all the vertices are connected, you can notice that the total number of edges are n minus 1, means if there are 5 vertices, then total edges are 4. Now let us take an example to illustrate the concept of the Prim's algorithm. Apply the Prim's algorithm on the following given graph, which is undirected weighted graph. And obviously we have to find the minimum spanning tree with its total weight. We can start from any of the vertex of this given graph, but suppose we start from the vertex G. So we highlight the vertex G in red color. Now we have to find the next vertex that can be attached with this vertex G. So there are 4 neighboring vertices of vertex G, and these are A, B, E and F. Out of A, B, E and F, we have to find the minimum weight edge so that we can decide out of these 4 vertices which vertex can be connected to the vertex G. So we find the minimum weight. Minimum of weight of G to A, G to B, G to E and G to F. And this value is 2. and 2 is corresponding to the edge G to A. Therefore, the next vertex that is connected to the G is decided and it will be A, and it can be connected to G through a edge GA. So we have connected GA. Now GA acts as a subgraph and we have to find all the neighboring vertex of this subgraph GA. So for this purpose, we have to find the neighboring vertices of node A and neighboring vertices of node G. When we find the neighboring vertices of node A, we see that there are two neighboring vertices B and G, but G cannot be considered as a neighboring vertex of the vertex A because AG is a single system or it is a subgraph. G is a part of the subgraph GA. Therefore, we cannot consider G as a neighboring node of node A. Therefore, the only choice that remains for A is B. Now we come to node G. Node G has four neighboring vertices A, B, E, and F, but A cannot be considered as a neighboring vertex of G now because G and A are part of a single system. Therefore, we consider GB, GE, and GF only. So the total neighboring nodes for both the system, both the nodes A and G, or we can say the subgraph GA are B, E, and F only. So we highlighted in the yellow color. Now we have to find which of these vertices can be connected to the subgraph GA. So we find the weight of G to B, G to E, G to F, and A to B. And these weights are 4, 5, 3, and 1 respectively. So obviously 1 is the minimum value and 1 is corresponding to the edge AB. Means the next vertex that is to be connected to the subgraph GA will be definitely B. So connect this vertex, we get this type of subgraph. Here there are only two systems. One assembly is GAB and other assembly have four different nodes F, E, C and D. And out of these four nodes, we have to select any one node and attach to this subgraph GAB. At every step, this subgraph is extended. Now for GAB, we find the neighboring nodes. The neighboring nodes of vertex B are C, E, and F, and the neighboring nodes of vertex G are E and F. So we highlight these two. A has no neighboring node because both its neighboring node G and B are part of the subgraph GAB. Therefore, A has no new neighboring node. So out of these C, E, and F, we have to decide which vertex is to be connected to the subgraph GAB. So for to decide this, we have to find the minimum weight. So we find the minimum of G to E, G to F, and then B to C, B to E, and B to F. These weights are 5, 3, 3, 4, and 1. Obviously, 1 is the minimum value, and which is corresponding to the edge B to F. Means the next vertex that is that can be connected to our existing subgraph GAB will be F, and it can be connected through the edge B to F. So connect it. Now it is connected. Means our subgraph is extended from GAB to GABF. Now we have to find again the neighboring vertices of this system GABF or this subgraph GABF. A has no neighboring vertices. G has only one neighboring vertex E. B has C and E as a neighboring vertices, and F also has only one neighboring vertex E. Now we have to find the minimum weight. So we find the minimum of BC, BE, FE, and GE. These weights are 3, 4, 2, and 5. So 2 is the minimum of these values, and 2 is corresponding to the edge FE. Means the next vertex that is to be connected to this subgraph GABF is E. So highlight E also or connect E also. So our subgraph is extended from GABF to GABFE. Again, we have to apply the same procedure and we have to find the next node that can be connected to this existing subgraph GABFE. So we find the neighboring nodes. B has neighboring node C only. The vertex E has two nodes C and D as a neighboring node, C and D. Now highlight these in yellow color. So find out of C and D which vertex is to be connected to the existing subgraph GABFE. So we find the weight of B to C, E to C and E to D. So this is total 3, 6 and 5, and out of these 3 is the minimum value which is corresponding to the edge BC. Means the next vertex that is to be connected is the vertex C and it can be connected through the edge BC. So connect BC also. Now the graph is extended to GABCFE. The neighboring node of the vertex C is D only, and also the vertex E has only one neighboring node D. F, G, A, B have no neighboring nodes because all their neighboring nodes are parts of the subgraph GABCFE. So highlight these E, D and CD and find the minimum weight. So out of 1 and 5, 1 is the minimum value which is corresponding to the vertex D and it can be connected to the existing subgraph through the edge CD. Therefore connect it. Now all the vertices are highlighted, means all the vertices are processed, and 1, 2, 3, 4, 5, 6, 7. There are 7 vertices. And now you can count the total number of edges are 1, 2, 3, 4, 5 and 6. N minus 1 edges. For n vertices, there are n minus 1 edges, means we have to stop our processing now. And we get our desired minimum spanning tree like this. So this is the minimum cost spanning tree or minimum spanning tree. And the weight of this minimum spanning tree is 2 plus 1 plus 1 plus 2 plus 3 plus 1, means total of 10 units. Now it is a time to give you a practice problem. So you have to apply Prim's algorithm on this given undirected weighted graph, and obviously you have to find its weight also. For your convenience, I have given its answer in the next slide. The weight of this graph is also 10 unit, as we have get in our example. So this is the overall concept of the Prim's algorithm. Thanks for watching this video, and I hope you will understand the concept of the Prim's algorithm very clearly. So please like, subscribe and comment on my channel Easy Learning with Krishna. So thank you once again for watching. Thank you.